So FINI. Finite fields. We'll go to in more details about some basic properties. Now let us recall that uh, how we constructed field of complex numbers from field of real numbers, right? On real numbers, we saw that there are equations like x square plus 1 is equal to 0 has no root. We attach the root. Suppose I is the root of means I square plus 1 is equal to 0, right? Such that A and B are reals, right? So this is how we constructed field of complex numbers. Sorry, this is field of complex numbers from field of real numbers, right? So in the same manner, we look at binary field, right? And and we take the equation x square as x plus 1 is equal to 0. Attach the root alpha. So suppose alpha is the root of this equation. And we got field with 4 number of elements a plus alpha b, such that a, b are in Z2. So this is your recall from the very basic lecture on finite fields when we talked about finite fields. So given a ground field, you look at a irreducible polynomial in this ground field which has no solution in that equation. Okay, and we need to keep in mind that the degree is important when we want to construct a field with 4 number of elements. So that is gf2 square. So we should take degree 2 polynomial. If we want to construct field with 8 number of elements, then we need to take degree 3 polynomial over gf2 or z2. Okay. So in general, we know that field with q number of elements looks like 0, 1, alpha 2, alpha q minus 2. 0 is the additive identity and 1 is the multiplicative identity, right? You can write down alpha is as power of alpha as well. Q is a prime power. So now we are going to look at some properties of finite. So let us take beta to be a non-zero element of GFQ, field with Q number of elements. Note that sometimes we also denote it by FQ or GFQ. The order of beta If beta is any non-zero element in GFQ, the order of beta is the smallest positive integer m, beta raised to power m is equal to 1. Okay, that is known as order of the element. Next, a polynomial is said to be irreducible if it cannot be written as product of lower degree polynomials. Right, so that is the, then we call that the polynomial is irreducible. If p is the order of beta, then it's q minus 1. Why is that? Because GFQ star is a multiplicative group of order q minus 1. So from POD group theoretic point of view, order of an element divides the order of the group. Okay, so that's the result. In any GFQ, there are one or more elements of order q minus 1 called primitive elements. So elements for which order is q minus 1, they are called as primitive elements. So let us take an example of G5. That means we are looking at G5 or Z5. Elements are 0, 1, 2, 3, 4. So 1 raised to power 1 is 1. So order of 1 is 1. 2 raised to power 1 is 1. 2 square is 4. 2 cube is 3. 2 cube is 3. 2 raised to power 4 is 1. So order of 2 is 4. Similarly, this is same thing as order of 3. And order of 4 is 2. So 2 and 3 are primitive elements. Okay. So 2 and 3 are primitive elements. In fact, we have a general result which I should mention here without proof, of course. The number of elements of order T is given by Euler Gaussian function. Phi of t. What is phi of t? Let me explain to you. Phi of t is nothing but, so if we write down numbers from 1 up to t and look at how many numbers are there which are relatively prime. Okay. For example, if t is 10, 10 I have to compute. So we note that I have written all the numbers up to t minus 1 and then see how many of them are relatively prime to it. So we have 1, 3, 7 and 9. Okay. So basically we can say that phi of 10 is 4. In fact, we have a formula that phi of p, if p is a prime, will be p minus 1, which is clear because p is a prime number. So how many numbers which are less than p and relatively prime to p? In general, so of course we have phi of 1 as 1. In fact, we have a general formula that phi of t is equal to t partial product p divides t. P is a prime 1 minus 1 over p. So phi of 6 can be written as phi of 2 into 3, which can be written as 6 times 1 minus 1 by 2, 1 minus 1 by 3 is equal to 2. Okay. Check phi of 15 is 8. And in fact, if m and n are relatively prime to each other, then phi of m into n the same thing as phi of m into phi of n if GCD of m and n is 1. It's a multiplicative function. Then the number of elements in GFQ of order t is phi of t. This is a nice formula. Let us take another example. In GF16, which is GF2 raised to power 4, we know that we construct this using a polynomial 1 plus x raised to power 4. Alpha square, alpha raised to power 4 are primitive elements, while alpha raised to power 3 and alpha raised to power 5 are not. So the order of alpha square, alpha raised to power 4 is q minus 1, that is 15. Okay. A polynomial having primitive element as a zero or root is called primitive polynomial. Okay. A polynomial having primitive element as a zero or root is called a primitive polynomial. Another fact, FQ star. FQ star means we are deleting zero. Star is a cyclic multiplicative group of order p raised to power m minus 1 or q minus 1. Okay, so that means it has a generator. Now, this ensures, as a corollary, very important result that every element beta of FQ of order p raised to power m, which is q, satisfies this identity beta raised to power p raised to power m is equal to beta, or in other words, beta raised to power q is equal to beta, or in other words, beta raised to power q minus beta is equal to 0, or you can say that beta is a root of x raised to power q minus x, right? In fact, what we can write down that x raised to power q minus x is same thing as x raised to power p raised to power m minus x is same thing as partial product beta in fq x minus beta. This is a very interesting result that every element beta of the finite field of order q satisfies the identity beta raised to power q is equal to beta. So this, I think you can prove it. I leave it as an easy exercise for you to show that this is the case. Okay, so you can consider beta raised to power q since the order of beta is q. So we know that beta raised to power q minus 1 will be what? 1, right? So it's easy to prove. Next result, again I am writing as a fact. In GFQ, there are exactly 5 of q minus 1 primitive elements. How many primitive elements are there in any field? Exactly 5 of q minus 1. Okay. Next, a primitive element alpha is an element of order q minus 1, right? We know that the order of alpha is q minus 1. In other words, alpha raised to power q minus 1 is equal to 1. Okay. Another interesting fact, A finite field exists for all prime powers, right? So we exist all prime power p raised for m. Next, if alpha is primitive element, so is alpha inverse. Next, if px is primitive polynomial, pp, this implies that p star x, which is reciprocal of p, is also primitive polynomial. Okay. And finally, we have another result saying that number of primitive polynomial of degree m is equal to phi of q minus 1 divided by m. So these are some very basic properties of finite fields. I have given some of them without proof, but if you want, you can read them. If you want, you can read them in the book. Now, I'm going to talk about another very important concept known as minimum polynomial. MP. So there are two kind of polynomials. We saw primitive polynomial, and now we are going to talk about minimal polynomial. What is minimal polynomial? Now we know that if we take beta to be a non-zero element of GFQ, then beta raised to power q minus beta is 0, right? Right, every element satisfies this. So beta is the root of beta is the root of x raised per q minus x equal to 0. So this polynomial has root over GFP, right? And it's a monic polynomial, right? This is a monic polynomial. But beta may satisfy a lower degree polynomial, right? So such kind of polynomial is known as minimal polynomial. So we can define the minimal polynomial over GFP of beta is the lowest degree polynomial mx such that m beta is equal to 0. So this is known as minimal polynomial of beta. So beta satisfies is x raised per cube minus x is equal to 0, but it may satisfy lower degree polynomial. As an example, I am writing minimal polynomials without proof right now, but I will give you the proof later on. Example, in GF16, element is 0. I can write down what is the minimum x, 1, x plus 1, alpha, x raised to 4 plus x plus 1, alpha square, we have x raised to 4 plus x cube plus 1, alpha cube, we have x raised to 4 plus x cube plus x square plus x plus 1, and finally we have, I'll just writing for alpha raised to 5 is x square plus x plus 1, and so on. Okay, so now actually we are going to discuss of minimal polynomials. Properties of minimal polynomials. Call it mx. Okay. What is mx? Minimal polynomial of beta, which is an element in GFQ. First property, mx is irreducible. Minimal polynomial is irreducible. Okay. Proof is very simple. Suppose mx can be written as product of two polynomials m1x and m2x of lower degree, right? Okay. Then what will happen? So degree of m1x is less than degree of mx, degree of m2x is less than degree of mx. Suppose this is there. But then I can compute m of beta, okay, which is 0, is equal to m1 of beta into m2 of beta. That means this product is 0. That means either beta is a root of this, either m1 beta is 0 or m2 beta is 0. If m1 beta is 0, that means beta is a root of a polynomial lower of lower degree than mx. Similarly, in case of m2 beta, there is a possibility that beta, so that means beta is a root of a polynomial of degree lower than mx. In both the cases, we are getting contradiction because we know that mx is the lowest degree polynomial that beta specifies, right? So this contradicts that mx, because mx is the lowest degree polynomial for which beta is a root. So this is a contradiction. So this is not possible. So mx is irreducible. Second property, if fx is any polynomial, this is very interesting fact actually. Fx is any polynomial coefficient in GFP such that beta is the root of this polynomial, then mx will divide fx. Okay, so note that mx is a lowest degree polynomial that beta satisfies. It's a minimal polynomial. And if beta is the root of some other polynomial, okay, then mx must divide fx. This is also a very interesting fact, and proof is easy. So let us see the proof. By division algorithm, we can write down fx is equal to mx into some quotient polynomial ax, or I can call it as qx. Qx is a better notation. Qx plus rx, where degree of rx is less than degree 8. Right? Now, put x equal to beta here on both sides. So 0 is equal to f beta is equal to m beta into q beta plus r beta. This is 0. This implies that r beta is 0. So r beta is 0 means beta is the root of a polynomial of degree less than the degree of mx, which is a contradiction, right? So then that means rx must be 0, right? This implies that fx equal to mx into qx. That is mx divides fx. Okay. Third property, mx divides x raised to power p raised to power m minus x, or mx divides x raised to minus x. Same thing, because q is p raised to power m. Now this is true because of m2. Why? Because beta is root of this equation, x raised to power p raised to power m or x q minus x. Okay, so we can take fx as this polynomial. Okay, I can treat it as fx. Then using property 2, since beta is the root of mx, mean mx is a minimal polynomial, it will divide this, right? So this is straightforward. Okay, fourth property, says that degree of minimal polynomial cannot exceed m. This is also an interesting result. Let me show a proof. We know that GFQ or GFP raised for m is a vector space of dimension m over GFP. This field we can treat it as a vector space over the ground field, right? Of dimension m. Therefore, any m plus 1 elements such as 1 beta, beta square, beta raised to power m are linearly dependent, right? Any m plus 1 elements such as this will be independent. This implies that there exist scalars ai in GFP, not all zero, such that summation ai beta raised for I is equal to or 0 to m actually is 0. This implies that summation I is equal to 0 to m ai x raised for I is a polynomial of degree less than or equal to m having beta as a root. Therefore, degree of mx we can think of is cannot exceed m. Okay, next property, fifth property, the minimal polynomial of a primitive element of GFQ has degree exactly m. This is an interesting result. So in general, the minimal polynomial has degree at most m. If beta is some root, if beta is an element in GFQ, but if beta is a primitive element, so minimal polynomial of primitive element has degree exactly m. Okay, and such a polynomial is called as primitive polynomial. Primitive polynomial. So how do we prove it? Okay, now beta is primitive element of GFQ with minimal polynomial mx of degree d, suppose. Okay, this mx will generate. We know that mx is irreducible, right? Let field of order p raised to power d. Okay, but this field contains beta. This implies that all of gf p raised to power m, therefore d will be at least m. Now we know that d cannot exceed m from the previous fact. This implies that d is equal to m. And that's all. Next property, sixth property, beta and beta raised to power p have same minimal polynomials. So I think I will give you an outline of this actually rather than proving it. In particular, over binary field, beta and beta square have same minimal polynomial. So proof is by example. I will give you a proof. So let beta is an element in Z of 16 has minimal polynomial x raised to power 4 plus x cube plus 1. Then beta square raised to power 4 plus beta square cube plus 1 will be 0. This implies that beta raised to power 4 plus beta cube plus 1 whole square is 0. Okay, because of field of characteristic 2. This implies that minimal polynomial of beta square divides x is power 4 plus x cube plus 1. Okay. Similarly, we can show that minimal polynomial of beta divides minimal polynomial of beta square, and hence they are same. So beta and beta square are known as conjugates. You can think of, in case of complex numbers, that there is a conjugate, if you know that on real or complex numbers, if we take a equation and if a plus ib is a root, then a minus ib is also a root, which is a conjugate. In the same manner, here beta and beta square conjugates to each other. Okay. Now I'm going to, these are certain basic properties. I'm going to talk about what is known as cyclotomic cosets. This is a machinery which can be used to construct minimal polynomials. So let Px be a minimal polynomial of alpha in GFQ. This implies that P of alpha is equal to 0. What about other roots of alpha? So conjugates of alpha alpha raised to power q, alpha raised to power q square, alpha raised to power q raised to power d minus 1. This is known as conjugacy class of alpha. Alpha with respect to GFQ. So the partition of powers of by the conjugacy class is called the set of cyclotomic cosets. Cyclotomics means circle cutting. Okay, so I think let me give you some example here. In case of GF8, 0, 1, 2, 4, and 3, 6, 5. So let us see how do we get. We look at the set Z p raised to power m minus 1 multiply by p divides Z raised to power p raised to power m minus 1 into cosets. So the cyclotomic coset containing S is like S, PS, P square S, P cube S, and so on to P raised to power M S minus 1 into S, where MS is the smallest positive integer. Okay, such that P raised to power MS into S is congruent to S modulo P raised to power M minus 1. Okay, so let us take a very specific example. P is equal to 2. So we are looking at modulo 15, suppose. Okay, M is equal to 4 here. So cyclotomic coset containing 0 will be singleton 0. C1 will be 1. P is 2 here. So 1 into 2. Then 2 into 2 is 4. 2 into 4 is 8. 2 into 8 is 16. Modulo 15 is 1. So we are left with this. C. Now what is next is number is 3. So we will take C3 here. 3. 3 into 2 is 6. 6 into 2 is 12. 12 into 2 is 24 modulo 15, which is 9. Similarly, C5 is 5 and 10. C7 is 7, 14, 13, 11. Okay. So these are the cyclotomic cosets. Okay. So I think we take another one actually when p is equal to 2 and we are looking at modulo 7, suppose. So C0 will be 0. C1 will be 1. 1. Sorry. 1 into 2 is 2. 2 into 2 is 4. 4 into 2 is 8. Modulo 7 is 1. So 1, 2, 4. Then we are left with C3, right? C3 is 3, 6, and 5. 3 into 2 is 6. 6 into 2 is 12. Modulo 7 is 5. Okay. So these are cyclotomic cosets. And I think now using this, we can actually construct some minimal polynomial and so on. So in case I will write down for G of 8 what we are going to do. This is the example of G of 8, right? So conjugacy classes, order, minimal polynomial. When the conjugacy class is 0, order is nothing, and we have x as a minimal polynomial. 1, x plus 1. Now you see that what are the powers here? 1, 2, 4. So 1 for 0, we got this one. Alpha raised to power 0. This can be written as alpha raised to power 0. Here, alpha raised to power 1, alpha square, alpha raised to power 4. Order is 7. And you can say that I can find out polynomial for x plus alpha into x plus alpha square into x plus alpha raised to power 4. And the next one, alpha raised to power 3, alpha raised to power 6, alpha raised to power 5, 7. So this is nothing but x cube plus x plus 1. The next one is x plus alpha raised to power 3, x plus alpha raised to power 6, x plus alpha raised to power 5, which is nothing but x cube plus x square plus 1. So essentially, this also gives a factorization of x to the power 7 plus 1 as x plus 1, x cube plus x plus 1, then x cube plus x square plus 1. Okay. So actually, cyclotomic cosets are very important here to do the factorization, okay. Anyway, so that's all for today. We'll talk more about the finite field properties in the next class. Thank you.